Did you know that diamonds, coal, and graphene, as well as like buckyballs and stuff, this is all just different forms of carbon. Carbon hooked up in different ways. We call these carbon allotropes. And really at their heart, they're just carbon that's making different attachments to other carbons, as well as some like impurities and stuff when it comes to the coal. And we'll talk about how there are different levels of coal with more or less impurities. But the ways that these carbon atoms are hooked up to one another is going to influence the structure and the properties of these different materials. That's why diamond is so much different than graphene, but they're both made up of carbon. In the case of a diamond, each of those carbon atoms is bound to 4 other carbons, and you get this tight network in this really strong material. In graphene, as we'll talk about, you have these like sheets of carbon, and each of those carbons is only bound to 3 things, but carbon can form 4 bonds because it has 4 valence electrons. Don't worry, we'll get into this. But basically, you have extra electrons that are going to be shared between these sheets, and this allows them to conduct electricity, and it also allows these like sheets to kind of like come off of your pencil and onto your paper. And finally, we have, well, I guess not finally, there's like other weird like nanotubules and things like this, which take advantage often of the graphene's ability to have this like electricity flow, because when you have those delocalized electrons, those shared electrons, well, they can move around, and the movement of electrons is electricity. And so these carbon materials are like all the buzz for like nanomaterials and stuff like this. And then you have coal. So coal is actually like amorphous, which means it doesn't have a defined structure, unlike those other types of carbon that we talked about. And because it doesn't have this like defined structure, it's just kind of like blobby, it can incorporate impurities into that structure. So in like a diamond, there's no room for impurities because each of those carbons has to be bound to 4 other carbons, and that's all it can form. And so you get this tight like network where you have this like strict structure. But in coal, you can incorporate these impurities in there, and this is actually one of the biggest problems when it comes to actually burning coal, is that these impurities then get released. And the way these impurities get incorporated is because coal forms when like peat, so like dead plant material and stuff, kind of gets like lower and lower, like higher pressure it goes, and it goes like down and down and down, like in the Earth's crust and stuff. I don't know about the crust, but it goes down in the earth, and basically the pressure builds up and the heat builds up and all of this stuff, and it makes it so that this carbon molecules kind of like come together. But so there's bunch of other stuff around because this is coming from like dead plant material and dead animals and stuff. So you have all these other elements, things like sulfur and that sort of thing, and then these can get incorporated into that coal. So the deeper down you go, the higher the pressure, the more those impurities are kind of like squeezed out. But and this will give you like a higher quality coal, whereas like higher up, like newer stuff that hasn't had as much pressure is going to give you a lower quality coal, which is going to have less carbon and more of those impurities. So we'll talk more about this as well as these different carbon allotropes, but we need to start at the basis of all of this, which is why carbon wants to form like 4 bonds, why it'll have an extra electron if it only forms 3, and that sort of thing. So let's go and talk about the atomic structure of carbon as well as all other elements. So carbon is an element just like nitrogen, hydrogen, oxygen, all these other things you'll find on this periodic table. These all represent different elements. And these elements come in these basic building blocks, these atoms. And each of these atoms is made up of even smaller parts. These are what we call subatomic particles. These are the positively charged protons, the neutral neutrons, and the negatively charged electrons. The protons and the neutrons hang out in this dense central core we call the nucleus, and then whizzing around are electrons and these negatively charged electrons. And those electrons are going to be the way that these atoms interact with one another. So basically these electrons, we can't know exactly where they hang out, but we can kind of predict where they're most likely to be. And we can represent them as kind of having these shells structure where they have this like shells of an onion where you have these different kind of layers of electrons. Now, this is not how these orbitals are actually like laid out and stuff. This is not how things actually are, but it turns out that this is a really helpful way to understand how these atoms are going to react, because for reasons outside the scope of this post, atoms will react in a way that will fulfill, like they'll give them their full outer shell of electrons. So you can think of each of these atoms as kind of having like an ideal number of electrons. And they can kind of get to that ideal number either by gaining or losing electrons or by forming covalent bonds. So a covalent bond is where basically these atoms kind of like overlap part of their electron clouds in order to share a pair of electrons. So it's one pair for a single bond, two pairs for a double bond, and this will allow them to help get to their ideal number. And their ideal number is going to be having what we call this like full outer shell. So this outer shell, these represents the valence electrons. These are the electrons that are furthest away from the nucleus. And why that matters is because the nucleus is where those protons are. And we have opposite charges attract, so the protons are going to be what's holding in those electrons. And so the further you're away from those protons, the weaker the pull you feel, and thus the more reactive you are, the more capable you are of like forming bonds or leaving and giving up, sharing, all these different things. Basically, these valence electrons are going to be the most reactive. And these atoms will react in a way that will get them to their ideal number of valence electrons. And the ideal number of valence electrons is going to be having a full outer shell. And so for most of these atoms that we care about in biochemistry, this means having an octet, so having 8 outer electrons. As you go across the periodic table, basically you're adding the number that you see here. This is the number of protons, and that's what defines the different elements. So carbon has an atomic number of 6. This tells you that it's always going to have 6 protons, but the number of electrons can vary. And because and then you can get like charges and stuff if you have an imbalance. But if you have a neutral form of carbon, you're going to have 6 protons and you're going to have 6 electrons. And so 2 of these are in this inner shell, and then you have 4 in this outer shell. And we said that carbon wants to form 8 wants to have 8 valence electrons. And so what it can do is it can form 4 single bonds, or it can form 2 single and a double, or 2 doubles. So basically in a single bond, you're sharing 1 pair of electrons, and in a double bond, you're sharing 2 pairs of electrons. And when you share electrons with another atom, basically you get to count their valence electron towards your outer shell. And so by forming these 4 single bonds, carbon is then able to fulfill its octets. So it's using like the 4 that it came with, and then it gets 4 more through the shared ones through the bond formation. So carbon is going to be able to form 4 bonds. And in diamond, each of those carbon molecules, each of those carbon atoms is going to form 4 bonds. And so each of these carbon molecules is attached to 4 other carbon molecules. And you get this very, very sturdy structure and this very defined structure, because in order to have all these carbons hooked up to 4 other carbons, they have to be in a very defined, orderly arrangement. And so diamond is going to be very strong, and it's also going to be very pure, because you can't let anything else into that organized arrangement, or else your organized arrangement is going to be disorganized. So diamond is very pure, and it's going to be very strong. Well, what about graphite? So graphite is made up of sheets of graphene. And in this graphene, each of these carbons is only bound to 3 things. And so it's forming these 3 single bonds. And if you have just 3 bonds, well, now carbon's still going to be left over with a lone electron. And atoms really don't like having like leftover electrons. And so what's going to happen is that electron is actually going to be shared among multiple, among like the carbons. And so it's forming these 3 bonds to other carbons, kind of like in a sheet. So it's attached to 3 other carbons. And then you can think of like above and below the sheet basically is this electronic commune where all these carbon atoms are kind of like sharing that leftover electron with all of the other carbons like all around it. So not just the carbon next to it, but like all of these. And so this is what we call like electron delocalization or resonance. So basically, in addition to forming these bonds, in addition to having lone pairs, basically electrons can be shared among multiple atoms. And we call this electron delocalization or resonance. We see it come up a lot in biochemistry and things like carboxylate anions and amide bonds, so like peptide bonds. You also see it in like aromatic rings, so the classic benzene ring, where you have basically this electron delocalization or this conjugation resonance, lots of different words for it. But basically, you have this electrons being delocalized, being shared among not just the neighboring atoms, but among a bunch of atoms. And so we call it aromatic compounds when it happens in a ring. But basically, what's happening is now the electrons can flow among all these different atoms. And in when we have this graphene, instead of just being able to flow around like a ring, it's actually able to flow like all the way between these sheets. So you can think of those electrons as kind of living above and below the planes of those sheets. And these electrons can be traveling through those like shared cloud, and this is going to allow it to conduct electricity because, well, electricity is the movement of electrons. And so if you have those electrons moving around, well, now this can conduct electricity. And because you have these, it's like planar, so it's like flat because it's kind of like in 2D. So you get these sheets with the electrons above and below the sheets. And so this is why, like in a pencil or whatever, you can like kind of sheets can come off onto your paper from your pencil, which can be helpful, but you might be wondering, okay, well, why don't those sheets just fall apart? And the reason why those sheets don't fall apart is something called van der Waals forces, or like dispersion forces. Basically, each of these, they're kind of like temporary charges that that set off a chain reaction, that all these carbons kind of get their electrons in sync for a second, and this is going to allow them to have like charge-based attractions that are just temporary. So a lot of what goes on in chemistry and biochemistry, basically a lot of the reasons why atoms and molecules do what they do is because of charge. So you have opposite charges attract and like charges repel. And this is true of even partial charges as well. And so we see partial charges in molecules like water, where you have a polar molecule, where those atoms are that are linked up through covalent bonds. If they don't share those electrons fairly, then you get partial charges, even in a neutral molecule overall, because the electrons are going to be hanging out more among near some of those atoms. And so this is why with water, you get this what we call polar molecule, where the oxygen's hogging the shared electrons is partly negative, and the hydrogens are left partially positive because they're having those electrons pulled away from them. Now, in the case of these carbon-based molecules, well, all these carbons have the same amount of pulling power, and so they're not going to be pulling unequally from one another, but they're going to be very equally pulling. So you get this really non-polar molecule where it's basically really blah, and so that you have this like you don't have permanent dipoles, you don't have permanent separation of charge, but that doesn't mean you can't get temporary separation of charge. And why this might happen is if we go back to our opposite charges attracting and like charges repelling, imagine you have just like a carbon molecule and something charged comes near it. Well, now the electrons that are near, so if something negatively charged comes near it, all those electrons that were on that side are kind of going to get shift over, and this is going to then make the ones next to it shift over, and so you get this kind of chain reaction where all of these are going to kind of get synced up, and you get this, now you have a dipole, a temporary dipole, you have this separation of charges, you have partially charged regions that are then going to be attracted and repelled to other molecules. And so you can get these attractions that individually they're really weak, but collectively they're really strong. And so if you think about having all these sheets with all of these atoms kind of like in sync, they're able to form these strong attractions, which is why like geckos can walk up walls and stuff, but also they can move their feet, right? And so you can remove those sheets because these interactions are like temporary, and they can easily be broken just by breaking like a single thing in the chain. You break the whole thing. And so you might be wondering, okay, well, where does that charge come from if all of it is just carbon? Well, it turns out that basically the electrons in these different atoms, they're moving around randomly. And so you might randomly end up with more of them in one area than in another area. And when this happens, well, now you have a temporary dipole, a temporary separation of charge that just happens by chance. But because it's been surrounded by all these different atoms, you're still going to be able to set off these chain reactions. And so you get these like dispersion forces, these forces where it's basically happening just like a random chance is happening. That's going to allow these partial attractions to form. But then remember that they're not going to be that they're very vulnerable. They can be very strong because you have so many of them. It's kind of like also a way to think about it is like, I don't know if you've seen that Mythbusters episode or whatever, where they like take phone books and they interspace, like take two phone books and then they like layer one paper on top of the other paper on top of the other paper. And like from one sheet to the other book or whatever. Hopefully that made sense. But basically you get all this like friction and stuff that you see, it's super duper sturdy. They were like pulling cars and stuff with it. It was crazy. But so individually, each of those that like if you only have like 2 pages, that'd be really weak, but if you have a bunch, it'd be strong. And so basically you can get these individually weak interactions to form a collectively strong thing. And so this is why the graphite doesn't just fall apart. Those sheets don't just come off, but they can come off and they can be used to make all sorts of different cool structures. So there's these things called fullerenes. And so these are basically carbon-only structures that have all these cool shapes like spheres or ellipsoids or tubes. And the walls are made up of these carbon rings. And with 5, 6, or 7 carbons. And they have a wide range of sizes. They have different names depending on like the shapes and the sizes. So you might have heard of like buckyballs. This is Buckminster Fullerene or C60. And its relatives, they're like highly symmetrical spheres. They look kind of like soccer balls. Then you have things like nanotubules or bucky tubes. These are like kind of like those sheets of graphene being rolled into a tube and then like capped with half a buckyball. So they're like 50,000 times smaller than the human hair, but they can be super duper long. Okay, well, super duper meaning like centimeter range, but which might seem really, really short, but if you think about how tiny their diameter is, then that's crazy. And you're thinking about like a single sheet of carbon. This makes them like super duper tiny and light and all this various things, but they're strong and they're efficient heat conductors. And so they're like all the buzz in nanomaterials and stuff. And then we have carbon nanobuds, which are buckyball-like buds that are covalently attached to the outer sides of a carbon nanotube. So you can think of having one of these tubes and then having these little like carbon warts on them. So those are the fullerenes. Okay, and so those were kind of like our more structured forms, but we can also have solid carbon that is unstructured. So that is what we call amorphous. And when you have this amorphous carbon, we call this coal. Well, at least if it has enough carbon. So you can think of like there's different classes of carbon. And so sometimes people don't even consider the lowest grade of carbon. So this like lignite, some people don't even consider it as being coal because it's only like 25 to 35% carbon. Some people say you need a higher percentage of carbon in order to actually classify as coal. But this lignite is a part of this whole like pathway in the making of like that really high quality coal. So, I mean, the earth isn't like purposely making this stuff, but what happens is that when plant matter dies, it gets buried over and it starts to decay. So that original stuff is not, the partly decayed stuff isn't coal yet. Instead, it's just peat. And so it's going to have a very small amount of carbonization. So basically carbonization when it's kind of like the carbons are coming together and pushing out the other stuff. We're going to see more carbonization as we get deeper into the earth and we get higher pressure and temperature. And we're kind of like kicking out the moisture and the impurities. But initially we just have this dead matter. It's going to start carbonizing a little. It's going to be spongy, and it can be added to the soil to store and release moisture and nutrients. Then as you start getting higher in pressure and temperature, now you get to lignite, which is the lowest rank of coal. And so this is about 50 million years old, and it's like crumbly and brown. So it's sometimes called brown coal or rosebud coal. And it's going to give you high carbon emissions when it's burned. If you go deeper down, if you go older, about 100 million years old, now you're getting higher amounts of carbon because you're pushing out those impurities. So this is like 35 to 45% carbon, and it represents about 47% of all the coal produced in the US. Go a little deeper, so we're talking older here because it takes a while for it to like get pushed down and for other stuff to build up on top of it. So now we're talking about 100 to 300 million years old. And now we have about 45 to 86% carbon. And this bituminous coal, it includes smithing coal, cannel coal, and coking coal. And then finally, if you go even deeper, now we're talking anthracite. And so this is the highest rank of coal. It's 86 to 97% carbon. It's going to be the hardest and the most dense. So think about like when you have impurities and stuff, it's kind of going to be breaking up the different carbon networks, making it so that carbon can't form as many carbon-carbon bonds. This is going to make the structure weaker as well as more porous and more able to like have stuff like soak into it and things. And have impurities in it. But as you get more carbons coming together, less of the other stuff, you're going to have a stronger structure. And so this anthracite is going to be the hardest and most dense of these. It's also going to be the most energy rich because, as we'll see, it's the carbon that's going to be giving us the fuel, giving us that sort of thing. It's going to burn cleanly with little soot. So you have, if you just have like pure carbon, well, now you're not going to have those impurities that are being released, but it's expensive, but it's used in like stoves and furnaces and things. So how you're actually getting that energy is through combustion. If you were to burn coal, basically combustion is when you use oxygen to break down coal into carbon dioxide, and it also releases energy as heat or light. But it also releases other pollutants. And so not only is the CO2 bad because it leads to like global warming effects and things like this, but the things that aren't carbon in there are going to be bad. And so basically you can have impurities, and just as we talked about before, these different levels of coal have different levels of impurities. And the more impurities you have, the bigger the problem this is. Because those impurities can then contribute to all sorts of other problems. So there are different kinds of impurities, but a couple common ones are sulfur and nitrogen. With sulfur, what you have to worry about is sulfuric acid, which can lead to acid rain. And then with nitrogen, you have nitrous oxide things, which can be respiratory irritants, lead to ozone and smog. So these impurities are going to be a really big problem from coal combustion, as well as the CO2 that it gives off. So even if you have the cleanest coal, it'll still have those impurities. Okay, but you might be wondering too, okay, well, what about diamonds? If we have it so that the deeper you go, right, if you went down further, would you get to diamonds? And the answer is no. Diamonds and coal are both made from carbon, but they're not made from one another. So diamonds form much, much deeper in the mantle part of the Earth's crust, where the pressures and temperatures are way higher. So the diamond formed deeper down. It's not forming because it got like pushed down from above. Instead, the way that diamond gets to the surface is it gets pushed up from below. So these diamonds typically formed hundreds of millions to billions of years ago, and then they only made it up to the mineable depths thanks to really deep volcanic eruptions. So they're starting where the pressure is really, really high, and the pressure and the temperature is really, really high and stuff deep in the Earth's crust. They're starting there. They're not getting pushed down. And then there's like a volcanic eruption, which then pushes them up. And when it pushes them up, now the diamond is traveling through all that other stuff in the soil, all that other impurities and things, but it can't incorporate it because, well, one, they're going really, really fast, and two, the diamond structure is so strong and there's no space in it for other impurities. And so you end up with these like pristine diamonds that are sitting there for millions to billions of years, which is really, really cool. And speaking of cool, a lot of early research on coal was done by Rosalind Franklin, and you might know of Rosalind Franklin. Hopefully you know of Rosalind Franklin from her work on photo 51, which was that fiber diffraction image of DNA that helped show that it was a double helix. Or I guess that showed that it was a double helix. And so much more on that in another post, as well as I have more detail on my blog and in another video of how Rosalind Franklin actually did some early research on coal, trying to figure out the difference between different types of coal and the different kind of structures within the coal. So really cool stuff about coal. And so remember, coal is amorphous carbon. So it's shapeless, or at least it has no defined shape. It has no defined structure. Whereas when we talk about diamond and graphite, these are in buckyballs and nanotubes and stuff. This is all like they have defined structures. And so these are all different like allotropes of carbon, which basically an allotrope is just a different structural arrangement of an element. And so in this case, our element is carbon. You can hook it up in different ways. Hook it up with 4 bonds, which is the maximum for carbon. So you get this like maximum sturdiness. With graphite, you have basically these carbons are forming 3 bonds, and they're doing so in sheets. And so you have these sheets of carbon with these electrons traveling throughout in between these sheets. And then with buckyballs and nanotubes and stuff, you have like rings, and you have sheets and stuff that are coiled, that are rolled up and form these like 3D structures, which can do really cool stuff. So that is the basics of carbon allotropes, and I hope it helped.